In lesson 3, we're going to be looking at different types of transformations, ones that produce congruent figures and ones that produce similar figures. So go ahead, take a look on page 23. The first thing you want to do is label the origin as point P, plot points M and N, and then connect the segments that they ask for. So go ahead and do that. Then come back to the video. So they ask you to plot this. Okay, so what you should have plotted, P, M, and N, connected the segments. So now they're starting to ask you about how do triangles PMB and PNB prime relate? So the blue triangle here and this orange triangle. So they had followed this rule up here to get point B, right? So they took the X coordinate of the B and tripled it. They took the Y coordinate of the B and tripled it. So B started at the point 2, 3, and now it is at the point 6, 9. So how do those two triangles compare? So it looks like they're dilations, like it's a dilation by a scale factor of 3. And looks like the point of dilation is point P, the origin. So a scale factor of 3, center at 0, 0. So then what must be true to the ratio of PB to PB prime? Okay, so comparing PB to PB prime. So must be in a 1:3 ratio because PB is coming from the smaller triangle and the bigger triangle is 3 times bigger. So this is a dilation, like we said, by a scale factor of 3, center, point P. So why does it make sense that the ratios of the legs of the triangle were both 1:3? Okay, which we didn't really look at both. But if we did, so this kind of shorter segment here is 2 units, and then this longer one is 6. This blue one is 3. Okay, this one is 9. So would those ratios be the same, and why? Well, we followed the same rule, right? So the rule was XY. So we took the X and tripled it, and we took the Y and tripled it. So that X distance is the horizontal, the Y distance, okay, is the vertical. So then this one was going to be 3X, and this one was going to be 3Y. So then they would keep simplifying down to the same ratio of 1:3. And then you do have the definition of dilation on your purple sheet as well. So does this match the definition of a dilation? Okay, and it does because it has this center point and then a ray that goes through it, connecting the image and the pre-image, or the image, the original figure and the image. Okay, and it's K times further, or 3 times further away. So go ahead on 3.2 and see if you can match each image to the rule. So here are the rules, and you want to match the image. And again, these are on page 24 in your workbook. So go ahead, figure out a strategy to match the rules to the images. Decide whether the image and the original figure are congruent. Are they similar, or are they neither? And then come back to the video and we'll discuss. All right, so we're just going to discuss this. Again, if you're at home, you'll just discuss it with yourself, or if you can phone a friend and discuss it. But let's discuss each match. So I've matched problem number 1 for you. So rule number 1, which was XY maps to X divided by 2 and Y divided by 2. So the X coordinate and the Y coordinate are both dividing by 2 in each one. Okay, so this was the 0.64 that mapped to 3, 2. Okay, and then 8, 4 half of each of those is 4, 2. 6, 8, half of each of those is 3, 4. So you're going to just talk that out however you figured it out. So I matched number 1 to image D because I noticed that the X's and the Y's are each half the size. Okay, so when I did this 8, 4, then I noticed that it's the similar point on the image was half. So it's 4, 2. So each of the coordinates were half of the original. Maybe you said something else. Okay, maybe you said for that one, I matched that because it was the only one where the image just got smaller, but didn't rotate or twist or move. So I knew it was just going to be half the size. There were only 2 images that got smaller, and this is the only one that didn't change position. The shapes in figure D are similar, okay, because their angles are still the same, but their side lengths are just half as long. So this is 2, this is 4, and this is a 90-degree angle. This one is 1, 2, and a 90-degree angle. So by side angle side, I see that those are similar. And it's a dilation because it has a scale factor of 1/2. So talk through how you matched up those other ones and then come back to the video. All right, so like we talked about, number 1 matched with image D, and we decided that it's similar. So you could have done a couple different things. So now I know I'm done with this one, so I don't need to look at that one anymore. So maybe you did some different things here. Maybe you looked at these A and B both kind of change position, like they rotate or twist or reflect, where C is the only one that looks like it just moves or just slides. So in looking at this, okay, that appears to be number 4, and it's just moving -4, -3. So maybe you looked at that, it moved to the left 4 and down 3. Or maybe you just knew this was the one that looked like a transformation from previous lessons, and these shapes are congruent to each other. Okay, because you see that all of the sides and angles stayed the same length. So now we figured out where C goes. So then trying to figure out A and B. Okay, it looks like this one kind of twists. So taking a look maybe at one of the coordinates, 1, 2, and then this goes to 2, -1 appears to be the point that goes with that one. So that's the Y becomes the X, and the X is the opposite of the Y. Or sorry, the Y is the opposite of the X. These kind of switch places, and it's the opposite of that X. So maybe you noticed that happening in this one. Okay, we put the Y first and then the opposite of the X second, and it appears to be congruent. Okay, they're congruent rectangles with side lengths of 1 and 2.5. And then this one, maybe you applied, and again, you could have applied this rule too, okay, to a different coordinate. So just pick a coordinate. Okay, so this one's -2, 3. So maybe you notice that this one just looks like it's changing size, but not at the same rate. So maybe you just noticed, okay, well, we only multiply the X here by 2, but not the Y. And I know that that doesn't produce the same sized shape. And it doesn't produce a similar shape either. So this is neither. We can see that since these legs are 2 and 2, and this is 1 and 2. Okay, that's just a couple strategies you could have used. Definitely could have done other things to match those up as well. All right, then page 26 in your workbook. So write a rule Okay, so write a rule that brings you from ABC to A prime, B prime, C prime. Okay, writing a rule is sometimes easier if you're describing in words what's happening. You could also write down the coordinates so you can kind of see what's happening. Okay, and thinking about that to write a rule, do that for DEF to its image as well, deciding if they're congruent, similar, or neither, and then come back to the video. All right, so when you're writing a rule, I sometimes find it easier to have the coordinates written out, okay? So you can kind of look at what's happening. So point A is the point 2, 3. And then point A prime, which is the one it's going to map to, is the point 2, 6. Because it does look like it's just moving up, right? But then we see that this one moves up 3 units, but this one moves, C moves up 4 units. So it's not just a translation. So let's write out the ordered pairs and see if we can see, okay? So we see this, kept the same X, the Y moved up 3, or we can see it multiplied by 2. So let's look at point B is the point 5, 4. And B prime is the point 5, 8. So then we can see, like we just talked about, that this is plus 3, but this is plus 4. And we know the rule has to stay the same. So it can't just be to move the shape up a certain number of units. So the other thing that we hopefully see that is similar is 3 times 2 is 6, 4 times 2 is 8. And then we can look at the C value and make sure. So this is the 0.34 to 3.8. So the Y value did, in fact, just double. So then our rule here would be that X comma Y maps to the same X value, but 2 times the Y value. So are these shapes congruent, similar, or neither? So I would say neither, because we only changed the Y value by a factor of 2. You can also see that the angles change. Specifically, it's pretty easy to see that angle B changes size. So this angle is much larger in this one. Okay, so right here is a lot larger. Could also compare the side lengths. Then let's write a rule for DEF. So again, it looks like it's flipping over. Okay, so it looks like it's kind of reflecting over the x-axis. So maybe you remember what that rule is. Maybe you want to write out the points. So D is the point -2, 1. D prime is the point -2, -1. E is the point 4, 3. E prime is for -3. And then F is the point -6, 1, and this is -4. And then F prime is the point -6, -1. So when writing that out, then we can see that the X coordinate stayed the same in each one, -2, -2, -4, -4, -6, -6. So the X stayed the same. So what happened to the Y? Okay, so again, maybe you're looking at, okay, that's -2, but then this is -6. So that can't be the rule to just subtract. Okay, but this did go from 1 to -1, 3 to -3, 1 to -1. So the Y value is just the opposite of what the original Y value was. And that will give you your rule. These are congruent. Okay, we see that the side lengths are identical, so you could go and calculate those if you wanted to, but it's just a reflection over the x-axis, so it's a rigid motion as well, keeps the shapes congruent to one another. All right, so you can look at corresponding side lengths and angles in them. Okay, so for the first set of shapes, okay, the corresponding sides and angles stayed or were different. They changed in this first one, but they stayed the same in the second one. How would a transformation look if it kept the angles the same but not the side lengths? So what kind of, if the angles stayed the same but the side lengths changed? So that's going to be some type of scale factor, right? The scale would need to stay the same. So we need to be multiplying the x and the y by the same amount. Unlike the one we looked at that just doubled the y, this is stretching it disproportionately. So that's going to change the size of the angles. Okay, so we would need to change the x and the y, or the horizontal and vertical distance, by the same factor in order to keep the angles the same. So is it possible to keep the side lengths the same, but not keep the angles the same? So this, I mean, feels like it wouldn't be possible. I would say for a triangle, not possible, because triangles have side, side, side congruency. So if they keep the same 3 side lengths, then the angles have to be the same. There's only one triangle produced. So I would say if we're talking triangles, that's a no. Okay, so if we're talking triangles, that's a no. However, with a quadrilateral, it's possible, because you could keep, so if we think of a square, you could keep all of the side lengths as 2, okay, but if it kind of crunched, okay, you could end up with, it's possible that you could end up with a rhombus that has all side lengths of 2, but now not right angles. So you've got right angles here, but these are not. So I would say absolutely not for triangles, but yes, you could probably do it for quadrilaterals and maybe some other shapes, okay, but definitely not using a rigid motion, okay, or a dilation. Because if you do a rigid motion or a dilation, okay, you're either going to keep everything the same, or you're going to make the sides bigger and the angles will stay the same. So not any of our kind of motions that we've been talking about. All right, so take a look at these 12 rules and decide, do you think it's going to be a rigid motion, or is it going to produce similar figures, or is it going to be neither? And let's do the most specific. They're either rigid, meaning they're going to get congruent shapes, or they're going to be similar, okay, or neither. And decide what you think for each one and then come back. All right. So these ones in kind of this form where we added a number to each the x and the y, we know create rigid motions, okay, because we know that they're going to be translations. So we talked about that rule that mapped xy to x plus or minus h and y plus or minus k, just moved the shape or translated it along the directed segment hk. So this one is going to be rigid. Let me get a highlighter instead. All right, so this one's going to be rigid. This one's going to be rigid. Okay, here we just subtracted 3, added 8. Okay, this bottom one subtracted 4, subtracted 3. So certainly those are all a bunch of translations. Okay, we also looked at multiplying the x and y by the same number. So in number 3, those just stretched the horizontal and vertical distance at the same rate. So that's going to produce similarity. This one's stretching at a different rate because the x is multiplied by 2, but the y is not. So that's neither. It's going to stretch it side to side. This one switched the x and y, but also multiplied the x, but not the y. So it's not changing it at the same scale factor. Down here, x3 means x times 3, y times 3. So same scale factor. Okay, different scale factor for the x than the y. So that's going to be neither. So let's look at some of these other ones. So this one switched and flipped the x. Okay, so we looked at this when we actually plotted this one, and it's a rigid motion. Okay, it just moved it. It kind of rotated it. ended up being a rotation. Same with this next one. We just flipped the X. That's a reflection. Just going to flip over the Y-axis. This one flips over the X and over the Y. So rigid. All right, so the summary here, if we plot a point and we just have the opposite of the X, opposite Y first and then X, and we kind of switch those coordinates around, what's that going to produce? Okay, so that's producing this kind of, let's see, DEF here from ABC. So moving from this blue one to this green one creates a rigid motion because the side lengths are congruent. We could quick do the Pythagorean theorem on the different sides here to come up with the length of each one and get that these two triangles are congruent by side, side, side. This next one, so from the blue to the yellow, here's the rule that we followed. We just multiplied the Y by 3, which just stretches it vertically, okay, but doesn't stretch it horizontally at the same time. So that's producing different sized side lengths. And it's also not, so it's not rigid for sure because it's creating a different size, but it's also not a dilation since the corresponding angles aren't the same. So here angle A went to this angle and that's much larger. Okay, B went to this angle Y and that's much smaller. Okay, so the angles changed. So it's not a dilation. So hopefully after this lesson, you can determine whether a transformation produces congruent or similar figures or neither. And you can try this cool down to see if you understand what you're doing. And if you are struggling with that, you can make sure you reach out to your teacher.